So in the previous class, we economic. So we said the economic is the graphical optimization method based on the truth table, which means that we start from truth table. The first based on the some logical sentences or some logical conditions, then we can generate truth table, right? So we can define the input and output signals, input and output values based on the some condition. And then so we are learning about the system, so which means the input and output don't have digital values. Okay. So we can define some condition, and based on the condition, we can define outputs. Okay. And then based on the truth table, I said that we can generate Boolean equation, but these Boolean equations are not optimized. So in order to generate the optimized circuit, we need to minimize the number of gates, right? Because in order to implement the gate, a digital gate, then we need to invest transistors. So that those are hardware resources. So using the economic, we can optimize the Boolean equation. Then when you generate the economic, then you need to remember, so like this, the truth table, we can define input signal and output signal. And then the economic, the row and column of the economic, then we can define the input values. And then you need to remember that, which is very important. We need to assign input values like the 0, 0, 0, 1, and the next value is 1, 1, not 1, 0, right? Because so when we use the economic, then we exploit the Boolean theorem, like the P A plus P A bar equal P, right? And then you have to use this theorem and these values. So the values of the input signal, the 0 and 1, if we assign the neighbor, so which means that if 0 is assigned, then the next column or next row will be 1. So you have to apply this theorem. So you need to remember this 0, 0, 0. The order of the input signal should be 0, 0, 0, 1, 1, 1, and 1, 0. So another point is that edges. Actually, edges of economic are connected to each other. So it means that this edge is connected to this edge. So this edge is connected to the lower edge. So which means that, so and then in order to apply the optimization, then I said that we need to generate the large circle, right? And then the number of elements in the circle should be power of 2. So at the edge, actually explaining this. So even though these elements are set apart, but we can generate the large circles within these elements. So suppose these are the connected this edge, the opposite edge. Okay, so you need to remember this very important. Sometimes you may forget this rule, okay, but it's important. Okay, then the economic includes non-care signals, then we can think non-care as 0 or 1. But actually, we can consider non-care as for the optimized way. So, which means that if we can make a larger circle or large rectangles, then we can think as these are ones, right? Non-cares are 1. Because non-care structure signals can be zeros or ones. Okay? But if we don't need to include this structure, then we can look at this structure is zero. So which means in this example, this structure is not included in the Hanuman. Okay, so this is also important. Okay, so this is the brief review of the Hanuman. And then I also mentioned that the goal of this course is to learn audio description languages. Okay, actually we will learn Verilog, system Verilog, okay, system Verilog HDL. So like the high level languages, or the high level language means that it's a kind of C or Python. Python is also the high level language, but Python is the interpreter language, not the compiler language. So usually, but our system, we just have the compiler type language. Okay, so C, Java, and some other languages. The Python is the interpreter based language. But so actually, so I introduced that the chip size. Recently, the chip size is very large, so which means that a single chip includes a large amount of transistors, billions of actually. So for CPU, a single CPU chip includes billions of transistors. Huge number, right? Billions means it's equivalent to 10 in Korean. So it's a large number. So actually, then in the first day of this course, I explained in the early stage of the actually long time ago, we just draw each transistor because a single chip includes actually in the long time ago, a single chip includes a small number of transistors. So we can draw it. We can draw transistors. It's not possible recently. So actually, when we build there's a chip, and firstly we design. We implement the functional design or logic design using audio description languages. And then these audio description languages are compiled and then synthesized into the circuit. Okay, like actually, we can build the very simple high-level model using the audio description languages, and then we can synthesize our modules, and then at the synthesis, so then the CAD tool is the tool, the EDA tools, the CAD tool generate the netlist. So netlist means that, so actually we seldom use these gates. We can define the behavioral or the structural model using the HDLs, the audio description languages. But actually, the chip vendors such as the TSMC or Samsung is the fab vendors provides the gate level modules. Okay. And then, so actually, at the synthesis, then our module is translated into the netlist, and then it's the compositions of gate levels, so the basic gates. So which means that simple modules are translated into multiple gates and then connections. And then the gates are just and or gate, exclusive or gate, right? It's a very simple gate. But in order to build the various chip, then we need to implement transistor actually, right? So physical design is that this level design is also translates into the transistor level design, right? Then actually, the this transistor level design are also very complex. So actually, the human cannot do this task. So we count on also that to EDC code. So actually, for this physical design in first part of the unit steps, like conditioning, group, and something like that. But it's related to the some low level design. It's related to the electrical engineering research. So we will not cover this part. And after that, we need to verify our chip. Because chip manufacturing is a very expensive task. So millions of dollars, so over millions of dollars. It cost over millions of dollars. So then after that, then we can sign up the our final design. Then these final designs are manufactured by fab, the fab companies such as the TSMC or some. Okay, so fabricated and then it's packaged, and then the chip is out. So this is the common process for implementing or for building various chips. Okay, let's learn about the hardware description language. So we can start from the definition of hardware description languages. So I copied this definition from Wikipedia, right? Then I highlight some important concepts in hardware description languages. So you can think that the hardware description languages are programming languages. So why do we use programming languages? So actually, computer just understand the machine code, and then the machine codes are composed of 1 and 0. But the problem is that humans cannot understand the machine code because we cannot understand the group of zeros or ones. So actually, we write the code in high-level languages. So high-level languages are very similar to our natural languages, such as English or Korean, not Korean. So actually, you cannot find Korean-based programming languages. So it's similar to the English language. So we can write our code using these high-level languages, high-level programming languages, such as C. So the problem is that a computer system cannot understand this high-level language code. It's just a text file, right? It's just the group of some English words in the English syntax, the programming language syntax. So it should be translated. The code between high-level languages need to be translated into the machine code. So we use a compiler, and then compiler generates assembly code based on the high-level language code. And this is the example of the assembly code. And then assembler generates the machine code based on the assembly code. Okay, and then as you can see, this machine codes are composed of many zeros and ones. The digital values, right? And then these codes are stored in the main memory of the computer system, and then a processor reads the machine code and then execute the defined instruction, right? That's how the programs are working on the computer system. But before the programs are working on the computer system, the high-level language code need to be translated. Also, it's the same for the design. it's very complex, and then we cannot, you know, it's very hard to understand this complex design, right? So actually, using hardware description languages, we write the code, and then this code describes the behavior of electric signals. Okay? So you need to focus on the actually HDL also includes the structural model, but the base model is the behavioral model. So HDL describes the behavior of electric circuits. So it means that behavior of electric signals. Okay, and then based on the simple modules, then we can also generate the complex module. So think about the hierarchy or modularity. And then based on the sub-module, we can generate the more complex, higher level module, right? This is the hierarchy and then modularity. And then, so we can also describe structural model using hardware description languages. So this is the main purpose of hardware description languages. So it's similar to the purpose of high-level languages. Why do you use high-level languages? Because you cannot understand the detailed machine code, detailed machine code. But if we write a code using high-level languages, then we can easily define the operation using the high-level languages. Also, we can understand the code more easily. So in order to understand the high-level language code, we also need to understand the syntaxes of the programming languages. But if we read the programming code, then we can easily understand this code, the operations of this code. So, and then operation is very similar to the behavioral model. Okay. So using hardware description languages, we can define behaviors of digital signals, like electric signals, right? We can define, okay? And then based on using the hardware description languages, we can also define some changes of electric signals, okay? So when we learned about the combination module, so when we learned about the combination model, combinational module or combinational block, this combinational block includes some components, right? Which require module need to define inputs and then outputs and then functional specification plus timing specification. So when we learned about the combinational block, then I mentioned that the combinational block includes these 4 components: input signals, output signals, and then functional specification, and then timing specification. Then using HDL, we can define these components, right? So since the combinational block, also we will learn about the sequential logic later. Sequential logic also need to include these components. So actually, it's a common part of this module. So in order to define the module or combination of logic module, then these components need to be defined. And using HDL, hardware description languages, we can define these components. Okay, so you need to remember input, output, functional specification, so it's a behavioral model, also timing. Timing can be also defined. Okay, so and then these are another some definition of the hardware description languages. Okay, so what can you see? What can you observe? So hardware description language, precise, formal description of an electric signal. So actually, with using hardware description languages, so we can define the behavior, the precise behavior of digital circuits. But it's an abstract term, which means that we do not describe the detailed behavior like the analog signals or analog behaviors. We cannot define using other languages, then we can define the analog behaviors, but in common HDLs such as the system Verilog and HDL, then we cannot define the detail. But using this HDL, we can define digital-based signal behavior. Okay, so precisely. And then why do you need to use HDL? Because if we design our hardware module using HDLs, we can simulate, we can analyze our design. Okay, so hardware description language codes for hardware description language modules are required for analysis. Okay, analysis of our design. Also, it is required for simulation. So what is simulation? So just to estimate the behavior, just to estimate the result of our system. That is the simulation, right? So it's not real behavior, it's not real result, but we just emulate, we just estimate the result or behavior of our system. That is called a simulation, right? So we can simulate our design. If our design is written in hardware description languages, then we can simulate the behavior of our design before making real chips, right? But you know, not to build a real chip, it costs very high. It means that actually over millions. Also, it's more expensive recently. So the cost is very high. But you know, the chips are VLSI designs are made by humans, right? So it means that bugs can be included because we are human. We are not a perfect man. We are not a perfect human. So actually, for every design, the bugs can be included. Then how can we debug? So it's similar to the software code. If we write a software code, then our code will include bugs, right? And actually, every code includes bugs. Okay, which means that we need to debug. We need to remove errors and bugs. How? We just run our code and then we just we can use some debugging tools such as GDB. But so actually, in order to remove bugs or errors, that we need to simulate. Which means that we need to run our design. So HDL code or HDL codes are required for also simulation. And then another important purpose of HDL coding is synthesis. So synthesis means that actually in this step, so actually using the HDL, so hardware description languages, we can design functional design code or logic design code. Okay? And then using the CAD2, so its step is called the synthesis. Our behavioral models can be translated into connections of basic logic gates. Okay? So these connections of basic logic gates are called listed. That listed. So actually the main purpose of hardware description language is to build real physical structures, which means that our code need to be translated for building real physical structures. And then for this purpose, we require the step code synthesis. Okay? So, and you can find one and this here. So we need to write a HDL code for synthesizing what? Synthesis. In Korean, it's called 합성, right? So, and then it means that our design can be translated into real data level. So it's a connection of simple logic gate can be translated into gate level design. Okay. And then gate level design can be also translated into physical design, the real transistor design, right? Then using this real transistor design, we can build real VLSI chips. Okay. That is the definition and properties of audio description languages. Okay. So it's a summary. So using the audio description languages, we can specify logic functions. So think like this. So you can just remember this for this module. It's a combinational module or also the sequential logic module. And each module needs to include the inputs, outputs, and then functional specification and timing. So and then I also explained that we use audio description languages to describe these components actually. Okay? Because each logic includes this component. So using hardware description languages, we can specify logic function, the function, right? Based on the input and based on the input, then we can define function of a certain module, and out will be generated from the inputs and then functions. Then action and then using HDL, we can describe behavioral or structural modules. Okay, that is the actual we can describe, and then using CAD tools, we can simulate our design, and we can also synthesize our design. So synthesize is similar to the translation. So it means that our HDL code can be translated into the gate level design. So names. Okay. So actually, the hardware vendors such as Samsung and then some to make a chip, the VLSI chip, then we need to use HDLs. Okay. Okay, and then I will introduce about several HDLs. Actually, there are two leading HDLs that are widely used. So the first one is the system barrel, and then the second one is the HDL. In this course, we will learn about the system barrel. So these are two leading HDLs. So actually, the for the programming languages, actually there are many programming languages, but in the HDL world, so there are two major audio description languages. Okay, so actually the industries where academia use these two leading HDLs very widely. Okay, the first one is the system Verilog, and then the Verilog was developed in 1984. This is a company, A2A Design Automation. And then as you can see, Verilog is specified by the specified as the IEEE standard. Okay, that is just a standard. Okay, so it's widely used and it's also specified as IEEE standard. And then actually the the Verilog is the original form of this IEEE standard. So this means that actually the Verilog was invented first, and then system Verilog was designed in 2002. So which means that in 1984, the Verilog was firstly designed as a Verilog. And then actually the system Verilog is the extended version of Verilog, but system Verilog is superset of Verilog. So which means that system Verilog includes every specification and then every standard of Verilog. And then system Verilog is the extended version of Verilog. So, but recently the system Verilog is more popular, also widely used. And then HDL. So as you can see, the HDL was developed it's developed by Department of Defense. So it's a Department of Defense. Okay, so it's developed by Department of Defense, and it's HDL is also part of IEEE standard. So standard hardware description languages. Then it's updated in 2008. In industry, system Verilog is more popular than HDL. So it is because Verilog is easier to learn. But Verilog is simpler than the HDL. So it's easier to learn. Okay. But the system Verilog or Verilog are widely used by some companies, industries. Okay. And then there are several other HDLs like system C. So system C, the C++ libraries. Okay. And then using the system C, we can describe the high-level behavior. Okay. So actually, there are some description level. They can be supported by each hardware description language. But for system C is very similar. Actually, it's right? It's a C programming language, and then system C, the C++ library. And then using system C, then we can describe the high-level behaviors. It's a system-like behaviors of the design. Okay. And then the advantage of system C is that we can use the syntax of C. Then we can describe the behavior of the system like C, the program language. Okay. And then another HDLs are Chijo. Chijo is based on Scala. It's not popular, but Chijo was developed by UC Berkeley. And then they are actually the RISC-V was also developed by UC Berkeley. So they are building some design using Chijo. And then BlueSpec is another high-level HDL based on Haskell. Okay, it's a programming language. And then also you can find the PyRPL based on Python. So, but these HDLs are developed by academia, so the university labs. So actually, those languages are not part of standard. So in the real actually companies academics widely use system error because these two languages are actual Okay. Then, as I mentioned, we can simulate our design. We can synthesize our design written in HDLs. Okay, I already explained about the simulation and synthesis. Okay, so also, but unit focus on synthesis and theory. It will be called when you use HDL, you think of hardware. It's so actually, so this is the example of the system level statement, the part of the code. So assign. So I believe everyone did. I hope everyone did the first design math, right? So if you see that this code, then this statement means C equal A plus B, right? So if we see this statement, this statement is very similar to C code, right? Actually, the syntax of system variable is similar to syntax of C. So C equal A plus B. It defines the behavior. So A and B are similar, and then this statement defines the behaviors of A plus B. A and add of additional A and B. But after synthesis, then this statement is translated into this analysis. So what can you observe? So these are synthesized gains. So A plus B is translated into many simple losses. So we can observe how everyday, so it's exclusive or so we can observe how small differences in particular number. And then also we can observe that these logics are connected to each other. Okay? So this is amazing, right? We just define the A plus B, but after synthesis, the CAD tools generate the NAND. NAND is the connections of basic gates. So which means that the basic gates are generated from this statement. Also, these basic gates are connected each other, and then this basically works like this behavior of C equal A plus B. Actually, it's atom. Okay, so using this circuit, then we can perform addition. Okay, we can this circuit supports addition operation. Okay, so think like this. So imagine that we can. So if we do not use the hardware description languages, then we need to build this next manually. It's very cumbersome job, right? It's also very difficult. And then the problem is that if we just connect to the long gate, the incorrect thing, so if we just connect the gates incorrectly, then it will generate bugs, the incorrect signals, incorrect result. But if we just define this C equals A, then it has two generator is logic gate. It's very simple and it's very convenient. Okay, so it's good. So that is, but if we just see that this programming language like statement, so we can think that hardware description languages are just programming languages. So, but you need to remember that we use HDLs for implementing hardware, right? So, which means that we need to remember that our model, our code will be synthesized, and then our code will be used for implementing hardware. Okay, so which means that actually the hardware, unlike the software is just executed from top to bottom, right? Like A equals B plus 1, B equals C plus 2, then B equals B plus 3, and like that. So if we just write our program language code, then each statement is executed from top to bottom. But if we write a code using HDLs, actually this statement is translated into hardware. And what's the hardware? It's connections of logic gates. Okay? So which means that it can be defined like the several logic gates are defined, and then several logic gates are connected to each other, something like that. So which means that executions of these logic gates are different from executions of software. The software just each statement is executed from top to bottom, but the executions of logic gates are determined by connections of input and output. Okay? So which means that even though we write a code like A equal B plus 1, C equal so B plus 1, and then B equals E equal A plus 2. Sorry about that. So B equal A plus 1 and A equal C plus 2. The execution of this code is different from the execution of software. What is different? So in this code, It's not a good example, right? E equal A plus 1. This is a good example. So the software, this statement is executed firstly, and then this statement is executed firstly. But actually, the hardware description language, this statement and this statement just defines the connections of signals. Okay? So which means that P equal A plus 1, A equal C plus 2. So if we just define some connections, so maybe the result can be the same, but we need to imagine connections based on this code. How? It looks like the C is plus 2, and then some signals are generated, and this is the A, and then A is given to the plus 1 module, and then B is generated. Okay, so which means that based on some statement, we simulate, and then we actually translate this statement into the connections of signals and then connections of functional blocks. Okay, you understand? So we think of the hardware as not synthesis. If we write a code using HDLs, there is important significant difference between normal programming languages and hardware description languages. So syntaxes are very similar, but we think of hardware description. How do you think of the hardware? Okay. So here we're treating HDL like a software and coding without thinking of the hardware. Okay. It's very important because we are learning about the hardware system, and then HDLs are used for describing behavior and then especially composition of hardware components. Because at the HDL code will be synthesized into hardware, will be translated into the hardware. So we think of hardware and you write the code in HDL. Okay. So this is the example. Actually, this is the hello world code, and then I gave everyone execute this code because this is the part of the level 1, right? The design level 1. So if you see this code, actually it will work, right? So it will work. Actually, in a software manner, so it will work. So which means that the hello world will be displayed. But actually, this code is not related to hardware model. It's just related. Actually, we can write a code using HDL. We can write the code like software like this. So this is the display command. There's this image, and then display command just displays these characters. Hello world on the screen. But this code is not related to the hardware. It is just the example code. Okay? So this code cannot be synthesized into hardware. This code cannot be synthesized. So using HDLs, we can write the code similar to the software, but this code will not be synthesized. Okay? So And then for that one, and I hope everyone can install the e-COSE value on your Windows or Mac OS system. And if you have some problem or issues, then please stop by TA's office, so you can post questions on Blackboard. Okay. So actually, it's very important. So in this course, we will learn about the system value. Then you require simulation tools such as COSE value. Okay. Okay, let's learn about the basic of system value. Okay, there are two types of module. As I mentioned, we can write a code for behavioral model. Also, we can write a code for structural model. So behavioral model just defines the behaviors of output, such as the C equal A plus B. So this statement just defines the behaviors of output C based on the input signals A and B. Right, C equal A plus B. But we can also build structural model using the system value. So I will show the examples later. But when you write a code, when you design a module using system value, then you can understand the module like this. Actually, this concept is very similar to the basic of combinational logic, right? So when you learn about the combinational logic, each logic includes the inputs, output, and functional specification and time specification. So when you write a code using HDL or system value, then we need to firstly define module. Okay, and then each module has the input ports. Okay, the ports. And then these are inputs. So ports is just the gateway to the module. Okay. So each module require input ports. So input signal via these ports. So we need to define input ports, and then this module will generate the output signal. So this is the output port. And then inside of the module, then we can describe the behavioral model, but we can also design structural model. Okay. System value. Okay, let's see the example. So this is the example of system value module. So the module starts with this module syntax. Okay. The module will start with the syntax module, right? We start with the module, and then after this module, then this is the module name. Okay. So which means that this module is the example module. So this is the module name. Oops. So example is the name of the module, and then as you can see, you can find some variables. So actually, the variables inside of brackets represent the port. Okay. And then so which means that this module includes the four ports being A, B, C, and Y. And then the input and output ports can be defined after this bracket. Okay. So I mentioned that when we design a module, and the module need to have input and output signals. So we can define input and output ports like this. Input ABC and then output Y. Then it represents this module, right? So the system variable module in example, then there are three inputs ABC and then there is one output Y. And then the definition. The functional specification or some structural model of the module will be here. Okay. And then each module need to be AND with the AND module. So this is the syntax of a system variable. So when we define a module, then the module need to start with module, okay, the syntax, and then the module need to be AND with AND module, okay. And then also the definition of ports can be inside of brackets. So it's a little bit different, right? So actually in this example, so I just list the ports inside the bracket, and then the properties of each port is defined at the bracket, right? But in this example, the port properties are also defined inside the brackets, right? So it's the same. It's the same. The model is the example, and then there are three input ports A, B, C. But these properties of signals are defined inside the brackets. Okay. So this is the another form of the module definition. Okay. And then we can add behavioral model inside of system variable module. So what is this? You can find that assign Y. So you can this is the output. So Y. Output Y is equal to blah 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 blah. Okay. So as you can see, input signals A, B, C are used, right? A, B, C's are used for generating output. So actually this is the Boolean equation. Then and then and this particular is the operators of system variable. Okay. So I also list some operators of system variable in the lab document, right? And then theta represents the NAND, then this is the OR. Okay. So what does that mean? This is the A. So actually, so this term represents the A and bubble, B and bubble, C and bubble, and three input AND, right? So using the system variable operator, we can define the Boolean equation or the behavior of logic very easily, right? We can define the output Y using the system variable operators. Okay. And then if the functional specification is defined inside of a system variable module, we can simulate this module, right? Also, in the first lab, I also provide the test branch file, and you can also generate the waveform using the COSE variable, right? That is the task of the first lab. So, like this figure that we can simulate our design. How can you see? So this is the input A, input B, and input C, and output Y. Okay? And then, what is this axis? So this means the time. Okay? So this is the hardware design. So which means that hardware works in the real world. Then real world includes time, right? So it works in the time domain. So as time flows, then the input signals can be changed. And then if input signals are changed, then output signals are also changed by the function of its functional specification. Right. So, and then if we simulate the our module, then we can generate waveform like this. Then, so they said it's a simulate, so which means that the input signals are defined by time, and then this input signal is given to our module. And then by time, the input signals are changed, and we can observe output signals are changed. And if we see this waveform, and we can check output signals are correctly generated based on the input signals, right? So by simulating our design, we can check the correctness of our module. Okay, we can check the waveform like this. So that's why I make you generate a waveform using COSE variable. Okay. And also our module can be synthesized. Okay. So this module can be synthesized like this. Okay. And then for synthesis, we can use the CAD tools. For example, Synopsys Design Compiler. So this is not the open source program. So that actually it's very expensive. So this data side design flow is very require the high cost. It requires high cost. So we can use the CAD tools such as Synopsys Design Compiler to perform synthesis. Okay. So if this module is synthesized, then the logic gates are generated, and then the basic logic gates are connected to each other. Also, the good thing is that so we learned some optimization method using Kanoman. So and then I mentioned that optimization is required to optimize the digital circuit, which means that we need to reduce the number of gates. The good thing is that if we write a code using HDL, and then its code is really synthesized, then optimization is also applied during synthesis. Okay, so it is done by CAD tools, not manually. So this means that even though we design the very not optimized logic or not optimized hardware, this hardware can be optimized. This hardware can be optimized during synthesis. Okay, that is good actually. But even though our design can be optimized during synthesis, we need to design optimized code actually, because it is based on our model, our behavioral model. Our model is not optimized, and result can be optimized. But it's simple. The simple code can be optimized well. Okay. Also, we can make a system value code for structural modules. So this is in this example, you can find many modules here, and then actually in the same file, we can include multiple modules in the same file, right? Like this. So in this example, you can find the module named end3, and then module named inverter, input, and then module named end3. And then you can find the definition of a module like here and here. And then let's see the end3 module. So if you see the end3 module, you can find that on end3 includes the 3 input signals and then 1 output signals, and then 1 internal node. Okay. So actually inputs are defined here, output is defined here, and then also inside of the module body, you can find the internal node like logic and 1. So this is the internal node. It's not an input, it's not an output. It's the internal signal or internal node. And then if you see the body of the module and the tree, then you can find the and the tree module is inserted, so which means that actually this is called the this is called instantiation. So it means that we can use end3 module as an instance in end3. So this is the instance of end3, which means that end3 module is included inside of end3. So it looks like this. Oh, this is the end3. And then end3 has the 3 inputs A, B, C. But inside of the end3, we have end3 module. Okay? And then these input signals are connected to the input of end3. Okay? And then output, so you know the output is the Y. So N1 is located with the output of the N3, so which means that this becomes the N1. Okay? And then you know the N1 is connected to the input of inverter. So inverter is instantiated, and then actually this is the instance name of the N3, and then this is instance name of the inverter. So N1 is connected to the input of inverter module, right? So this is the inverter, INV. So N1 is connected to the input of inverter. And then what is generated? Y. So Y is the output of end3. So this is the Y. So output is connected to the output port of end3. So in this example, we can find that in order to build the end3 module, we just instantiated end3 module and inverter module. Then we can just connect the input port to the input of end3, and then also internal logic is defined, internal logic is connected to the output of energy, then this actually node is connected to the input of inverter, then output of inverter is connected to the output of main three. Okay? So this is the example of a structural model. So structural model, which means actually a PAM module include multiple sub-modules like the AV3 and inverter, include the multiple sub-modules, and then signals are connected to the multiple sub-modules. So by this, we can build PAM module to the AV3. This is the structural model of system variable. Okay. So and then this is the some another. So actually, you need to remember that the system variable is the case sensitive, so which means that the uppercase and then lower cases are equal, which means that in this example, the reset and reset R, uppercase R and lowercase R are equal. So not the same signal. It's similar to C. C is also sensitive. So and then the module names cannot be started with numbers. Okay? This is invalid. So MUX 2 is okay, but 2 MUX is not okay. Okay? Name need to be started with alphabet. Then white space is ignore. And then for comment, you can use the dash or single line comment or multi-line comment. So this is plain to the C, right? For C comment, you can use the two dashes, two slashes. And then also you can use the multi-line comment. Okay? This is the additional syntax of the system variable. Okay, so I will stop here. So we learn about the basic of system variable. Okay. Any questions? See you in the next class. 감사합니다.